But it had an improper integral, so I threw it on there. All right. The limit as x approaches 0 of sine of x over x. We've seen this 1,000 times. Talk to me. 1. And we know it's 1 because I asked you to memorize it in August. And we also now know it's 1 because of L'Hopital's rule. If I were to take the derivative of the top, take the derivative of the bottom, we'd be cooking and we'd go. Let's look at the second one. If I plug in, do you all agree I get 0 over 0?
Yes.
It's not doing it.
Here, I'll get you a good pencil.
Yeah, just anything but what's happening right now.
Oh my gosh. Literally, it's like not even.
Okay. Can we agree that I can do L'Hopital's rule? I can derive top, derive bottom, plug and chug, and get 2.
Yep.
Or we used to be able to factor. This was x minus 1, x plus 1. And we cancel, and we're left with that. So when we plug in, we get 2. Either or, it doesn't matter. All right, let's look at the third one. I have e to the x minus 1 over x squared. Well, if I take the derivative, if I plug and chug, do we agree I get 0 over 0?
Yes.
If I take the derivative, it's going to be the limit as x approaches 0 of e to the x minus 1 over 2x. Well, we've got problems. Because if I plug in 0, I still get 0 over 0. So I do it one more time, and I know for a fact it's one more time because what's the bottom now going to be?
2.
Can I ever get 0 on the bottom?
No.
So this is just e to the x. Hey, this is 1/2, and we are cooking. Questions? Okay. The fourth one, I've got to infinity now. Well, if I plug in infinity, can we agree that I get infinity over infinity?
Yep.
Indeterminate form, so I go to L'Hopital's rule, and as I take the derivative, I'm left with 1 over x, 1 over 2 square roots of x. Well, if I go to reduce this, can we agree that this is the limit as x approaches infinity of 2 square roots of x over x? Keep, change, flip, right? Well, if I plug and chug straight up, we've got issues. We get infinity over infinity, but can't I reduce this? What can I reduce this to be? X to the 1/2 on the bottom. Do we agree with that?
Yes.
And if I do that, then I have 2 over infinity, right? And that is?
Attention teachers, please allow current 10th graders to attend the AP meeting in the auditorium. Thank you.
All right. So we're pretty good with limits, right? Hopefully. Okay. So what is an improper integral? What makes an integral improper? It is going to be an integral that has an infinity as a limit. So anybody that has an infinity as a limit will be improper. Or it's an integral, and this is the one that's in disguise, with an infinite discontinuity in the range of your limits. So two things make something improper. One is that you're going to infinity or negative infinity. And one is that the integral's limits has a vertical or discontinuity of some sort in between those two limits. So integrals with infinite limits are very obvious. You can see that it is an improper integral. It's the ones that are in disguise, the ones that are numbers, that have some kind of discontinuity in between the two values. So those are going to be a little bit trickier to find. All right, go ahead and write that integral down. We're going to watch, first block said they wanted to watch the video. So we'll watch, it's almost a 4-minute video, Khan Academy, of course. But he explains to us how we're supposed to solve if it is an improper integral. So let's see if this pops up.
Bless you.
Bless you, my dear.
We would say that it is divergent.
Thank you.
Figure out is the area under the curve y equals 1 over x squared with x equals 1 as our lower boundary and have no upper boundary. Just keep on going forever and forever as it really is essentially as x approaches infinity. So I want to figure out what this entire area is. And one way that we can denote that is with an improper definite integral, or an improper integral. And we would denote it as 1 is our lower boundary. We're just going to keep on going forever as our upper boundary. So our upper boundary is infinity, and we're taking the integral of 1 over x squared dx. And so let me be very clear. This right over here is an improper integral. Now, how do we actually deal with this? Well, by definition, this is the same thing as the limit as n approaches infinity of the integral from 1 to n of 1 over x squared dx. And this is nice because we know how to evaluate this. This is just a definite integral where the upper boundary is n, and then we know how to take limit. We can figure out what the limit is as n approaches infinity. So let's figure out if we can actually evaluate this thing. So the second fundamental theorem of calculus, or the second part of the fundamental theorem of calculus, tells us that this piece right over here, so let me write the limit part. So this part, I'll just rewrite the limit as n approaches infinity of, and we're going to use the second fundamental theorem of calculus. We're going to evaluate the antiderivative of 1 over x squared, or x to the negative 2. So the antiderivative of x to the negative 2 is negative x to the negative 1. So negative x to the negative 1, or negative 1 over x. So negative 1 over x is the antiderivative. We're going to evaluate it at n and evaluate it at 1. So this is going to be equal to the limit as n approaches infinity. Let's see, if we evaluate this thing at n, we get negative 1 over n. So we get negative 1 over n, and from that we're going to subtract this thing evaluated at 1. So it's negative 1 over 1, or it's negative 1. So this right over here is negative 1. And so we're going to find the limit as n approaches infinity of this business. This stuff right here is just this stuff right here. I haven't found the limit yet. So this is going to be equal to the limit as n approaches infinity of, let's see, this is positive 1, and we can even write that minus 1 over n. Of 1 minus 1 over n. And lucky for us, this limit actually exists. Limit as n approaches infinity, this term right over here is going to get closer and closer and closer to 0. 1 over infinity you can essentially view as 0. So this right over here is going to be equal to 1, which is pretty neat. We have this area that has no right boundary. It just keeps on going forever, but we still have a finite area, and the area is actually exactly equal to 1. So in this case, we had an improper integral, and because we were actually able to evaluate it and come up with a number that this limit actually existed, we say that this improper integral right over here is convergent. If for whatever reason this was unbounded, we couldn't come up with some type of a finite number here, if the area was infinite, we would say that it is divergent. So right over here we figured.
Okay. Here's where we're going to let it go. He has just told us that the area beneath a curve that is going towards infinity, hence there's no chunk, right? We're used to going from 1 to 5, from 2 to 6. We found Riemann sums. We did the area of a finite chunk. We said was a number, right? That would make sense. But he has now told us that this curve goes on forever, never stops, and the area is what?
It just looks like that.
Well, it just gets small.
It just be like that.
Okay.
Yeah.
So what's crazy here is that you're all like, oh, okay, if that's what I gotta let go, I gotta let go, no problem. I can do this.
But wait for it.
But wait, there's
You call
more.
now.
Okay. Algebraically, I think he did a very good job. He explained it perfectly. It was very nice. We all hopefully understood why the answer was 1. And we feel pretty good about it. So we're going to do it really quickly, so you at least have it on your paper. We're going to just solve it. And then we're going to go to the but, what if? All right. So the first thing he did on his chalkboard, whatever he's using, he said that we have to transform this into a limit. And this is key. On a free response, I have seen this on free responses before because this is tied into series, which is why we're doing it now. With the integral test, you have to put a limit here. We cannot take an integral of something that is not a definite integral. So the fact that this is 1 to infinity is not a definite integral, if you will. So we're taking the limit as n approaches infinity. Now, why is n such a common value? You'll see it in every textbook. When you guys did series and sequences back in the day, you typically used n as one of your variables. And so I think that's pretty much why every textbook kind of sticks with n with series, and that's why this guy has an n. You pick any letter you want, just don't pick x, okay? So we have the limit as n approaches infinity. He said this numerous times. You need to keep writing that limit until you actually take the limit. Boy, that sounds familiar, doesn't it? I used to say that all the time. Don't not write the limit. Don't let go of the limit until you have taken the limit. So he integrated this, and I think we all agree that it was negative 1 over x. And we are going from 1 to n. He said this was the second part of the fundamental theorem of calculus. He was not wrong. As n approaches infinity, we plug and chug our top minus our bottom. He said that this would be 1, and it's 1 because this is a negative and this is a negative. And then he said that if I were to take the limit as n approached infinity, this would be 0, and my answer is 1. Anytime, you're going to hear this for the next couple weeks, anytime you get a finite number, it will converge. If it's heading towards infinity, it will diverge. So this would converge, and you'll see it on the AP. They'll use it very interchangeably. Converging, convergent, converges. Any form of part of speech of converge they'll use. So that was good. That was no problem. Yes, ma'am.
So whenever it's like a definite number, like
A definite number. Any number is converging. Very good. All right. So the previous example, he had it drawn very nicely, was 1 over x squared. And he said that as I go from 1 to infinity, that area ended up being an actual finite number of 1. You all agreed. You all were like, okay, I can let this go. Okay, I'll figure this out. But I'm throwing now 1 over x at you, and 1 over x looks, good Lord, very similar to 1 over x squared. And this is 1 to infinity. So the question here is this also going to be 1? And let's talk about it.
no. Because calculus is hard to
So the limit as n approaches infinity is going to go from 1 to n of 1 over x dx. The one we just did, the integral was negative 1 over x, but Miss Brianna says this is not 1 over x. This is 1 over x to begin with. So Miss Brianna, what's the integral of 1 over x? ln of x. And right now, we start to see this is not looking good. This is not looking promising. Because now what do? I got to do my FTC, right? I got to take the limit as n approaches infinity.